So on Friday we looked at some polynomial theorems. Now we're going to look at some polynomial results. Here's some interesting facts. Whee. Okay. If a polynomial has k distinct zeros, so in other words, k solutions to the equation if you were to solve it, then we know that k minus each one of those will be a factor. Because remember, when we solve equations, we'd say, oh, that factor equals 0, gives me the solution x equals a1 or x equals a2, and so on. So for every solution, there must be a corresponding x minus that solution as a linear factor. Therefore, if I was to get all of those solutions and multiply them together, that must also be a factor. It's exactly the same as numbers. Like you think of the number 12. You know 3 is a factor of 12. You know 2 is also a factor of 12. Therefore, 3 times 2, 6, is also a factor of 12. So you can always build by the prime factors. So all right, show that 1 and negative 2 are zeros. Well, we can use our factor theorem that we saw the other day for that. And hence go and factorise this particular polynomial. So polynomial 1 substituted in, yep, equals 0. And polynomial negative 2, yes, that also equals 0. So I know x minus 1 is a factor, x plus 2 is a factor, therefore x minus 1 times x plus 2 is a factor. That's going to help me in my factorisation. So x to the power of 4, I'm going to write down, instead of writing down x minus 1, x plus 2, I'm going to write down the quadratic factor when we get that, x squared plus x minus 2. Because that's going to make life easier, because now I can use that idea of, well, leading term times leading term must give me the leading term. So the x squared must have been multiplied by x squared to get x to the power of 4. The constant times the constant must give me the constant. So negative 2 times something gives me negative 10. So that must be plus 5. All right, we now need to work out the x's. At this stage, we have how many x's? It's not a trick question. If we were to expand that out, how many x's would we get? How many do we need? So it seems to imply that there's not a middle term there. Because if I was to put an x in there, then that negative 2 would be times however many x we've got to create more x's. Now I've got 5x, that's what I want. We can double check. Let's pick another one. Do you want to check the x cubes or the x squareds?
Why not both?
Okay, good idea. Let's do both. If we were to expand out at the moment, how many x cubed would we have? And how many do we want? So that's okay. Let's have a look at the x squareds. How many would we have? Yeah, so we've got 5x squared minus 2x squared. So everything adds up. So we have no more terms in that second one. So there's our factorisation. X minus 1, x plus 2, x squared plus 5. Remember, of course, you could just do a polynomial division if you prefer, and you'd find the other factor is x squared plus 5. Okay. Now, slightly different to what we just said. This time I'm saying the polynomial is of degree n, and I know n solutions. Well, therefore, I must have all the solutions. You can never have more solutions than the power. Because think about it, if you're going to factorise it and make it x minus one solution, x minus another solution, and to expand out, that would become x to the power of n. If I was to add another solution on, then the power of x would increase. But we've said the polynomial is of degree n. So you can never have more solutions than the power, the highest power. So if I know n solutions, not only when I multiply those together do I get a factor, but it must be indeed the polynomial itself. And that's what I just said. A polynomial of degree n cannot have more than n. Well, I said n solutions, but using technical terms, n distinct real zeros. So, okay. We know a polynomial has a double zero at -7. So if we were to draw it, we know it would just touch the x-axis. when we factorize it, the double zero means it would become x plus 7 squared. And a single zero at 2. Write down a possible polynomial. So now x minus 2 is a factor, x plus 7 squared is a factor. Now yes, that is a possible polynomial, but I want to generalize this to come up with a statement that would create every possible polynomial. So what I'll do is I'll multiply it by another polynomial. However, I need to put a condition on that polynomial. That polynomial qx cannot have a solution of 2 or negative 7. Because if it did, say it had a solution of negative 7, then negative 7 would no longer be a double zero, because I'm creating another solution to become a triple zero. Same with 2. If I had a solution of 2, it would no longer be a single solution. It would become a double solution. So I need to write that condition down. There's another condition. I'm going to multiply it by k. K is just some real number. Because who's to say it's monic? So instead of multiplying out and get x to the power of something, I might get 5x to the power of something, or 10x to the power of something. So any multiple of that polynomial would still have solutions of 2, negative 7. So that would cover every possible polynomial. All right, what if I said it was a monic polynomial of degree 3? So again, we'll put down the two factors that we know. What's the degree of the polynomial at this stage? What was it, sorry? 3, yeah. If we were to expand that out. So it's already of degree 3. They've told me it's monic. So there's nothing more I can do to that one. There is, in fact, only one solution that would satisfy those requirements. What about a monic polynomial of degree 4? All right, we just decided that makes it a polynomial of degree 3. How could I turn that into a polynomial of degree 4? Yeah, so we know it's going to be a linear solution because there's only one more solution. Let's call it x minus a. But again, a can't be 2 and it can't be negative 7. They can't be solutions to that particular one. What about if it's degree 5? What should I multiply it by? Because now there's going to be 2 more solutions. Yeah, well, that's the temptation, isn't it? To go x minus a, x minus b. But we're assuming, by doing that, you assume that that quadratic can be factorised. But maybe the quadratic can't be factorised. So it has to be multiplied by a quadratic. So you're right, x minus a, x minus b is a quadratic. But by writing it as x minus a, x minus b, we're assuming that quadratic could be factorised. So I tend to just go to qx, where qx is a quadratic or a polynomial of degree 2. And again, they don't have solutions 2 or negative 7. They might have, and when we start looking at extension 2 sort of stuff, they might in fact have imaginary solutions rather than real solutions. And I didn't say monic for this one, so again I could multiply it by some number. Here is where I now contradict myself. Because back in number 3 we said we can't have more solutions than the power. Now I'm saying, well, if it does have more solutions, then there's only one thing the polynomial could be. And that's what we call the zero polynomial. The zero polynomial, just like the number 0, is a very interesting character. It doesn't necessarily obey all the laws that we want it to obey. Because if the polynomial is 0, how many solutions does the polynomial have? Yeah, has an infinite number of solutions because 0 is always equal to 0. Doesn't matter what you substitute in for x, 0 will equal 0. So it actually has more solutions than its degree, maybe. What's the degree of the 0 polynomial? I said this is another problem, isn't it? The 0 polynomial, there it is, the number 0. What's its degree?
1.
You're saying 1. What's your reason?
Because 1, oh wait, I
No, say it. It's a logical answer.
Because 1 times something, it just makes it work.
Yeah, I mean, you could have said, I suppose that.
Oh, yeah.
Remember, any constant number, if I said to you the number 7, and said that's a polynomial of degree Correct. I was about to say wrong then. I'm going, no, that's right. It is right. Yeah. So logic says maybe that one's degree 0. But hang on, I haven't got any of them. Because couldn't I then do this? What's stopping me from doing that?
Nothing.
Yes, exactly right, 0. Well, nothing is 0. So there's nothing stopping me do that. But there was one little definition in our polynomial that at the time I said is trivial, but it's important. And that's why we have it there.
A polynomial cannot be equal to 0.
Right. Remember we said the leading term in our original definition, we said Pn cannot equal 0. And so that's why this 0 polynomial is weird. It's just weird. I have seen a question in a test, so don't get caught out by it, because it's a little trick question, which says, you've got to find a polynomial that has, it's of degree 3, but has 4 zeros. The only thing it can be would be the 0 polynomial. Okay. So don't get caught out by that. In the normal scheme of things, 99.999999999999999. Keep thinking nines for as long as you... Imagine there was a 9 there for every second you've been alive so far. 8, and then 8s, and so on. Like, will be normal polynomials. That's how rare a question it would be. But be aware of it. So if you do see it, and then you, as you're doing it, going, you mean person who thought of this. But anyway, so it was great timing. We're going to do this exercise. Exercise, as we know, jolly good fellow. Maybe that's in honour of our guest. We have exercise, jolly good fellow, because... Okay, good. All right.